Thank you for your kind introduction. My name is Toshiyuki Tsuchiya from Kyoto University. Today I'm talking about the tensile fracture of silicon nanowire, which is integrated into microscale structure. The test is done by using MEMS devices. As you know, silicon nanowire is going to be used in future. We're going to be used as a key component of future integrated devices. As you can see in this picture, the nanowire is integrated to microscale devices, which is going to be detected acceleration. And also this is used for the suspending structure, and the also used as a piezo-resistive strain gauge for detecting strain using these nanowires. In order to evaluate the structural integrity or reliability, we need to investigate the tensile fracture of these nanowires. So our research objective is to do a tensile testing of silicon nanowire, but this nanowire should be fabricated using a MEMS or integration process, and also this nanowire should be fabricated into the same layer as the MEMS structure is fabricated. So nanowire, in this research, nanowire is around 100 nanometer in diameter, few microns long, and MEMS structure, its thickness is around a few or tens of micrometer thick, millimeter square in area. This research, we have two aims. One is development of this batch integration process, and the other is also, of course, a mechanical reliability assessment of this nanowire. So the main topic of this talk is reliability assessment, but I will talk a little bit about the batch integration process that we have developed, and also we talk about reliability. So I'm showing the three methods of making nanowire onto SOI, silicon on insulator wafer, which has 5 micrometer in device layer thick. So first method is one step, we call it Bosch process, and this is combination of an isotopic dry etching process called Bosch process, which consists of etching and the passivation process, repeating these two processes. So first we make the resist using EV lithography, and then using Bosch process, the isotopic etching and the width of the wire is determined. Then after this process, we do isotopic etching using again dry etching process, and the nanowire is released. At that time, the wire itself is undercutted, so the final thickness becomes somewhat different. Then this is the resulted nanowires. The thickness is good, but the width is good, but thickness is larger. But this is not the actual thickness, but it has a remaining passivation film on the side. So actual thickness is like this, so which is around 800 nanometers. This is very simple process, but the shape or the roughness is very bad. So in order to control the thickness more precisely, we developed the second method. We call it two-step Bosch process. Again, this is a combination of isotopic etching and isotropic etching. First, we put on the EV resist for the mask, and Bosch process and isotopic etching with fine scallop to determine the width of the wire. Then we switch the recipe to make undercutting of the wire by changing the the length of times of the etching and the passivation process. So the wire is undercutted. Then by using isotopic etching, the silicon nanowire is fully released from the Then this is the fabricated wire. We can make a thinner wire, and the thickness control is good. But because of the Bosch process, there is a scallops or roughness on the sidewall. And you can find some damage on the sidewall. In order to remove this roughness, we proposed the third process. We call it one-step Bosch plus oxidation thinning. So after making a 800 nanometer nanowire, we oxidize the device wafer totally, and then remove the oxide. Sometimes we repeated this process to make a thinner nanowire. This is fabricated around 150 nanometer nanowires with 5 micrometer length. It has very smooth surface, but it's somewhat rounded. Then, so we are going to use this mainly for this wire, but we will compare other processes in terms of the strength. Then this wire is integrated MEMS structure. In this case, we integrated the wire with a tensile testing device using electrostatic actuation and detection. Here, we have it has a electrostatic actuator to generate a tensile force, and there is a displacement sensor, capacitive type displacement sensor to detect the displacement. The spec of the wire is here, and the device actuates max as large as 50 micronewton, and displacement resolution is around 1 nanometer. And the integration process consists of device fabrication process and the nanowire fabrication process, as I mentioned. And in between, we have passivation process to protect the MEMS structure during the nanowire fabrication process. So first, we fabricate the MEMS tensile testing structure. Then this whole structure is covered with oxide film. Then the position that the nanowire is fabricated is open, and then the nanowire fabrication process is proceeded. And this is a fabricated device, a part of the device. This is actuating COM drive, and this is a displacement sensor. Here we have a nanowire integrated to the 5 micrometer thick MEMS structure, and 150 or 100 or 150 nanometer in diameter nanowires. Then we did some tensile testing using device packaged. This is a capacitive detecting circuit, and by applying the voltage onto the actuator, we got output voltage change from the displacement sensor, capacitive displacement sensor. At the applied voltage at 35 volt, after that the output voltage is saturated. It means that the device is wire is fractured. So we can see the fractured specimen after the tensile test. By calibrating the output of the displacement sensor, we got the force displacement relationship of this wire, and by measuring the cross-section of the fractured nanowire, we obtained the stress-strain relationship of this nanowire. Young's modulus is well agreed with 1-0 direction of theoretical single crystal silicon modulus, and tensile strength is 2.6 gigapascal. In this case, the wire is ellipsoid shape. Thickness is 190 nanometer and width is 152 nanometer. We tested two-step Bosch process nanowire and 4 oxide thinning nanowires. As we can see, the tensile strength of oxidation thin nanowire has better tensile strength. But in some reports, the tensile strength of this kind of oxidized smoothened wires has better strength. So we think this value is lower than expected. Of course, because of the oxidation process, the strength is little bit improved compared to the Bosch process nanowire. So we checked the fracture surface. We found that the fracture origin, fracture initiated at the bottom side of the wire, and of course the Bosch so-called scallops made by the deeper etching process, roughness is removed, but by observing the top surface and side surface and bottom surface, we found that the bottom surface has many H-pit-like structures. The origin of pit-like structure is have not been well understood, but possible to the oxide precipitation during oxidation process, and also we suspect that the thickness of the nanowire, whole nanowire, is not uniform because of the first step of one-step Bosch process. So we need to, I think, in order to improve the strength, we need to consider this H-pit problem, and also we need to improve the uniformity of the thickness. Okay, this is a summary. We tested silicon, single crystal silicon nanowire using MEMS tensile testing device. In order to improve the strength, we need to control the thickness and also surface roughness during the fabrication process. And I would like to say thank you for the financial support and Professor Sumiga over there to taking fracture samples, same image of fracture samples. And thank you for your kind attention.